All right, guys, it's time for fun with math. And today we're going to talk about something called improper integrals. And we want to start this lecture with just a short review of limits involving infinity. And so let's just take a look at each of these limits and evaluate them. And the easiest way really to evaluate a limit involving infinity is to kind of treat infinity like a number, but be careful not to cancel. So it's more of using the idea of infinity to interpret your result and not so much to do algebra with infinity. So let's take a look at this first example here. And so the idea is just plug in infinity and think about what happens. So we get 1 over infinity squared, which, infinity is like this huge number you can't possibly ever imagine. Because if you imagined it, it wouldn't be infinity because you'd add 1 and it'd be bigger, right? So it's this huge number. So it's like 1 over a billion type squared. And so that's like the number 0. And then over here, we'll plug in infinity again. So e to the negative infinity. And on this one, the idea is what? This is like 1 over e to the infinity because of that negative exponent right there. It means basically put it in the denominator. And then this is like 1 over like some massive number, like 1 over a billion. So what is that idea? That's like 0. And you can kind of test these if you want on a calculator sometimes. So on your calculator, you can do stuff like 1 divided by, and then do second e to like a big number, like 100 or something. And you see get 3.7 times e to the negative 44. So it's like 43 zeros with a 3, basically 0.43 zeros and a 3. So super, super small number. And then for the ln function, what happens here when you plug in infinity? So you have ln of infinity. And then you have to kind of understand a little bit about how ln works. So the graph of ln of x basically looks like this. It has a vertical asymptote here, but what we're more interested in is the fact that it just continues to go up, but very slowly. Sometimes I tell you guys, like, it's ln, e to the x is like the fastest growing function you know. So ln is like the slowest growing function you know. In fact, if you do ln of e to the 100, it's actually only equal to 100 because we know ln of e to the anything is the anything because ln of and e are inverses of each other. But e to the 100, it's this magnificent number, so big that I don't even know if the calculator will be able to tell us what it is. Let's see. So second ln is e, and put 100 up there. And what does the calculator say? Yep, 2.68 with an e to the 43 here. So that's times 10 to the 43. So it's a 2 and then basically like 43 places afterwards. That's a huge number. But the ln of it is 100. You can even do the, I wonder what the ln of that would say. Let's see what it says. So ln, stop. ln of that number, does it tell us it's 100? No, it remembers it. It's 100. Okay, one last problem that's kind of tricky. So this one, plug in infinity. So we have tan inverse of infinity. Now this one's pretty tricky because I bet a lot of you guys don't know what the graph of tan inverse looks like. So let me talk a little bit about it. So to graph tan inverse of x, you kind of have to know how to graph tan of x. So tan of x, there's a vertical asymptote here and a vertical asymptote here, and it basically looks like an x cubed function, but it has these two vertical asymptotes right there. And then of course it repeats. So it just does this movement and then it repeats over and over and over again. And you have to know where the vertical asymptotes are. So they happen at negative pi over 2 and pi over 2. And you can kind of remember that because tan of pi over 2 is undefined. And so this is a graph of tan of x. Now, to graph tan inverse of x, you have to pick a piece of tan of x because you can't invert the whole thing because it's not 1-to-1. So you pick that one little piece, which is a 1-to-1 function. So for each input, yeah, you get an output, and that output's actually unique. So if you give me the output, I can tell you the input where it came from. And what you're going to do is you're going to invert it. So I don't know if you can see me, but the idea is the graph's on here, and you're basically going to flip it and turn it around. So when I do this, what I usually do is I kind of follow these vertical asymptotes. The vertical asymptotes are going to become horizontal asymptotes because the inverse just swaps out the x's and the y's. So now you have x here and y there. And then this was pi over 2. So now This has pi over 2, and this is negative pi over 2. And let's move it off of that vertical axis so you can put a negative there. So negative pi over 2. So those are the heights right there. And then when you take that graph and you invert it, what's going to happen is it's basically going to look like this. And that's a graph of tan inverse of x. And the reason why I need to know that graph and why it's so important, it's the only way I know how to answer this question, which actually comes up more than you would expect. So what's the tan inverse of infinity? Well, what happens as you go all the way out to the right? Well, watch what the graph does. It heads up towards height, pi over 2. Versus if you take the limit as x goes to negative infinity, oops, put a negative there, of tan inverse of x, this is going to be equal to then tan inverse of negative infinity, which of course is equal to what? So then you write the graph down to the left and it goes to negative pi over 2. So negative pi over 2. And so that's a tough limit if you don't know what the graph of tan inverse of x looks like, but now you do. And then there's some easy limits that I didn't really talk about here, but if you have a limit as x goes to infinity of like x cubed, you just plug in infinity, so it's like infinity cubed, which basically is infinity. All right, so let's move on to some problems here. So what we're doing today is we're actually doing something called improper integrals. So what the heck is an improper integral? So an improper integral, there's really two types. The first type has an infinity or negative infinity as one of its limits of integration. So we call these infinite intervals, basically. And these type of integrals are either going to converge or diverge. And our job is to figure out, is this integral converging? And when it converges, it should go to a number, or is it diverging, which means the integral is not going to settle down on a single number. And so that's one type of improper integral. And the second type, we call it discontinuous integrand, and it looks something like this. And so what does it mean to have a discontinuous integrand? It just basically means that if you try to plug in one of these limits in here, or sometimes the limit could happen inside the limits of integration, but if you try to plug in a number in here, it's really not going to be defined. It basically just blows up or blows down. In that sense, it has like a vertical asymptote there. And so we call that the discontinuous integrand, or basically it's just unbounded on the between those limits of integration or on a limit of integration. All right, so our job is to get through at least one of these today. So hopefully we can get through part 1 here, and then we'll come back and do part 2 later. And so let's take a look at some of the examples here. So we're going to do 3 examples today. And so here are 3 examples. One has positive infinity as a limit of integration. The second has negative infinity as a limit of integration. And then the third one uses negative infinity and positive infinity. So you have like a double problem. So what do you do with that? So let's just do this first problem and try to make sense of, or try to figure out how do we make sense of an improper integral here. So we're going to determine whether the integral is convergent or divergent, and then find the value and find its value if it converges, right? So we're going to find the actual value if it converges, and then we'll use a calculator to draw a picture of the shaded region to check any work. And actually, we're going to start with that so you can kind of see the idea. So let's graph this thing. And so to graph this thing, I'm going to have to graph the integrand. And so this is the function, what? This is 1 over x cubed. And so I'm going to graph 1 over x cubed, so x raised to 3. And I only care about this thing going from 1 to infinity. So I'm going to go make my window go from 1. Oh, where's my window? There it is. From 1, and then maybe I'll go to like 100. Just something that's kind of big. You can do 1,000 or 10,000, but 1 to 100 seems big enough. And then I'll zoom fit it. So hit zoom, and then find zoom fit, or hit 0. I'll find it though. So there's zoom fit, hit enter. And you'll see this function basically kind of starts up and then comes down really quickly. In fact, I didn't even see how fast it came down. So I'm probably not going to draw it just like they have it here, but I'm going to go from 1 basically out to 100. And basically it starts up and goes down. And actually, what height it starts at? It starts at 1, because when you plug in 1, you get out 1 here. And then we can see what the integral if it's actually equal to something. So we'll hit second trace, and we'll go down to number 7. So we'll do this integral here. And then we'll just go from 1 to 100. Because we don't have an infinity button, basically. And so it kind of shades, you kind of see here, it shades in the region over there, but it spits out 0.4995. So basically, it looks like this area here should be 0.5. That's my guess. So let's see what happens. So the way this works is we got to turn this beast right here, this improper integral, into an integral that makes sense. And so how do we do that? Well, we just rewrite this integral as the integral from 1 to b, where we think of b as some number of 1 over x cubed dx. And so we're going to evaluate that integral. And then in the very end, we're going to take the limit as b goes to infinity. And so that's the definition of this type of improper integral. And so let's do it. So this is going to be equal to, and so this is the limit as b goes to infinity. And in order to integrate this, I need to rewrite this as x to the negative 3 dx. It's one of my types. And so that's equal to the limit as b goes to infinity of, and I'll add 1 and divide by it. So x to the negative 2 divided by negative 2 from 1 to b, which equals the limit as b goes to infinity of what? This is negative 1 over 2 x squared from 1 to b. And so now I'll plug in my limits of integration here. So this is going to be equal to the limit as b goes to infinity. I'll plug in my upper limit, so we get negative 1 over 2 b squared. And then minus, and I'll plug in my lower limit, so then negative 1 over 2 times 1 squared, which equals the limit as b goes to infinity. Let's just clean it up. So negative 1 over 2b squared, and then minus and minus is a plus, 1/2. And so now I can evaluate this limit just by letting my b be infinity. So I get negative 1 over 2 times infinity squared plus 1/2. And of course, this is like the number 0. Negative 1 over 2 times a billion is basically like 0. And so I just get back equal to 1/2. And that checks with my calculator. All right, so before you get too comfortable, don't worry. We're going to do it one more time here, actually a couple more times. So now we're going to switch over. And now I have negative infinity as my lower limit. So now what do? So to make sense of this thing, it's improper integral. What we're going to do is rewrite this as the limit as a goes to negative infinity of the integral from a to negative 2. And then we have 3 divided by, and I have 2x squared plus x minus 1 dx. And of course, I am making an assumption here that this denominator is actually defined. It's actually not equal to 0 between my limits of integration. So that's just assumed. If it was undefined, then we're in trouble. We have like a double type of improper integral. And so now, how am I going to integrate this guy here? And so the way I'm going to integrate this is I have basically a polynomial over polynomial. So this is a partial fraction. So let's check it out. This is going to be equal to the limit as a goes to negative infinity. And I have the integral of 3 divided by, and hopefully I can factor this thing on the bottom. So let me make this more space here. So it should be equal to something times something, and then dx. And for my something, you have to be a little bit careful because of that 2x there. So it's going to basically be 2x times x. That gives me the 2x squared. And this 1 right here, it's got to be a 1 and a 1. There's only one way to factor 1. And then to get the plus x, I need to make this a plus and this a minus. And the reason for that is I get 2x here and then minus x there. And so you can see now that my zeros happen at negative 1 and 1/2. So that the denominator is never 0 between these two limits of integration, a and negative 2, because they're to the right of negative 2. And so now I can rewrite this as being equal to the limit to my partial fraction decomposition. So a goes to negative infinity, the integral from a to negative 2. And it's going to be some number, capital A, divided by 2x minus 1, plus another number divided by b divided by x plus 1 dx. So everything looks good so far. Yep, everything looks great. And so now I got to figure out what a and b are. So I'm going to take this and set it equal to this guy over here. And so I have 3 divided by my 2x minus 1 times x plus 1. And I set that equal to this a over 2x minus 1 plus b over x plus 1. And I'm going to clear that denominator. So I'll multiply everything by a 2x minus 1 times an x plus 1. And so when I multiply it over here, I just get the number 3. And when I multiply it here, the 2x minus 1s are going to cancel, and I get a times x plus 1. And then plus b, when I multiply it here, the x plus 1s cancel, and times 2x minus 1. And then I can choose numbers to plug in for my x. So let's see, here I'm going to plug in maybe x equals 1/2, because that's going to make that 0. So that implies that 3 is equal to a times, and 1/2 plus 1 is 3/2, so 3 over 2. And then, of course, plus 0 when I plug in here. And so then I multiply both sides by 2, and I get 6 is equal to 3 times a. And so this tells me that my a is just equal to 2. To divide out both sides by 3. And then I'll plug in x equal to -1, because that makes this thing right here 0. And so I get 3 equal to, and so I have basically 0 plus, and then here I have b, and then 2 times -1 minus 1. And so 3 is going to be equal to what? That's -2 minus 1, so that's -3b, which tells me my b is actually equal to -1. And so now I'm going to come back over here, draw a line to kind of separate my work. And so this is going to be equal to the limit as a goes to -infinity, the integral from a to -2. And I have 2 over 2x minus 1, and then plus a -1, so that's a minus. Let's put a minus 1 over x plus 1 dx. So now I can integrate all this stuff out here. So it's going to be equal to limit as a goes to -infinity. And now it's ln, so it's going to be ln, absolute value of 2x minus 1. And that's actually the derivative. So you take the derivative of this is actually that. So it's 1 over the derivative of the insides times 2, and then minus ln, absolute value of x plus 1. And I'm going from a to -2. And so I'll rewrite that as the limit as a goes to -infinity, and I can divide these. So I have ln of 2x minus 1. I guess I should put that in absolute value. So let's do it instead of the absolute value of 2x minus 1 divided by x plus 1. And I'm going from a to -2. All right, so we're almost done. Well, we just need to plug in this upper limit here. So this is going to be equal to the limit as a goes into -infinity, a goes to -infinity of ln of, so we plug in the upper limit, you get 2 times 2 minus 1, which is 3, divided by 2, it's -2. Maybe I should go a little slower so I don't make silly mistakes, right? So let's just show us, I'll show you guys what we're doing here, right? So 2 times -2 and minus 1, divided by a -2 plus 1. And then minus, when you plug in a, so ln of, and you get 2a minus 1 divided by a plus 1. And so what's that equal to? It's going to be equal to the limit as a goes to -infinity of ln, and then absolute value, I have 2 times -2 is -4 minus 1 to -5 over -1. And then minus an ln of absolute value of 2a minus 1 over a plus 1. And now if you want, I can run the limit through this thing. So when you run the limit through this thing, I'm going to run it through this, and that's just ln of 5. And then minus, now I'm going to keep the limit on here, so I have the limit as a goes to -infinity, and we have to talk about what this is going to be equal to. Then I have 2a minus 1 over a plus 1. And so we talked a little bit about this in class. When you're doing limits that involve infinity, you can actually cross off these lower degree terms on bottom and top. And so this is going to be equal to ln of 5 minus the limit as a goes to negative infinity of absolute value of 2a over a. And of course, now the a's are going to cancel. And so this is going to be equal to ln of 5 minus the limit as a goes to negative infinity. I have ln of 2 left over. And of course, the limit of a constant is just a constant. And so what do we get? We get this to be equal to ln of 5 minus ln of 2, which of course is equal to ln of 5 over 2. And the question becomes, is that the correct answer or not? Is it ln of 5 over 2? So to see if it's correct or not, let me zoom out a little bit. And let's come back up here, back to this problem here, and let's use our calculator to graph this thing. And so where's my calculator? Here it is. All right, so let's hit y equals, because we can check our work. Last time we did this before we did the problem, so now we're just doing it at the end here. And so here I'm going to graph this. And so this is 3 divided by, and then don't forget the parentheses in the bottom. So left parenthesis and then 2x squared. And then plus x, and then minus 1. And then I'll make my window. So this goes from negative infinity to 2 to negative 2. So maybe I'll just do like negative, let's just do negative 10. Last time negative 100 seemed a lot. So let's just do negative 10 to, well, let's do negative 100. The farther you go out, the better approximation you're going to get. So I think you probably need a pretty decent, go out a decent distance. So negative infinity and then to negative 2. And then we'll zoom fit it. So hit zoom, zoom fit. We'll have to kind of pay attention to what's kind of happening here. And so it goes down. It should be way down here at the bottom. So it's way down here at the bottom, and then it heads up. So I'm going to graph this right here. Starts at the bottom, but then heads up. And in fact, it actually hits a point here, right there. And then we can shade in this region here. Right, so find that integral. So let's find that integral. And so I'll hit second trace, go down to number 7, that definite integral, and then do negative 100, enter, to negative 2, enter. And it should spit out some number. And the question is that number like ln of 5 over 2. So it gives us this number 0.90125, blah, blah, blah. So let's write that down. So 0.90125, blah, blah, blah. So that's the number it gives us. And the question is that number the same as that number or kind of close? As long as they're kind of close, you're okay. They won't be exact because you're only going to negative 100, but they should be kind of close. So let's check it out. And so I have ln of 5 over 2 in parentheses, and I get 0.96. Oh, okay, so 916. I'll take it, I bet if I go further out, I get a better approximation. So that's just to kind of verify my result. Now I should put on here that I went out to negative 100 and I'm going to negative 2. So I should put those numbers on there so it's clear how I found that value. Okay, so we have one last problem to do here. And this is an improper integral with double infinity. So you have a negative infinity and a positive infinity. And so to do this one, I'm going to graph it first. I should have graphed the other one first because it's just nice to see what it looks like, so you have a feel for what's happening. And so let's graph this thing. And so I'm going to hit y equals, clear that out, and then I have what? 1 divided by, and divided by what? Divided by x squared plus 36. So x squared plus 36 in parentheses. And so now I'm going to make my window go from, well, it's negative infinity to infinity, right? So I'm going to do negative infinity or negative 100 to 100 to see what that looks like. And then we'll zoom fit it, hit zoom, and then zoom fit. And if it converges, it's kind of has to go down on both sides and it can head up, but it has to go down on both sides. If it doesn't head to 0 on one of the sides, then it's not going to converge because you're going to have an infinite amount of area. So this one starts down here, kind of heads up, turns around, and goes back down. What's kind of nice about it is you see there's some symmetry on either side. It's actually an even function, so the height on either side is exactly the same. I actually know this height right here. It's 1 over 36, because if you plug in 0, that's what comes out of this thing, the integrand. And we went from negative 100 to 100. We can then shade in this region here and figure out what it is with our calculator. So I can hit second trace again and go down to that number 7, that definite integral, and plug in negative 100, hit enter, and then 100, hit enter. And you'll see we get another number, and I'm pretty confident that this is going to converge. Just the way the graph kind of looks makes me feel like it should. I can't always use that, but as a rule of thumb, it does typically converge if it looks like this. And so what do we get? 0.503 623. So let's write that over here. So you get about 0.5036 ... So that's just an approximation to that improper integral. And so let's go find it. And so it looks like, oh, and I forgot this one last step. I forgot to, so on here, we should write on here that, this converges. So that integral converges, this integral converges, because we found the number it converges to. So converges. And I'm pretty sure this one's going to converge, but let's see. So how do we turn this improper integral into basically a proper integral? We got to get those infinities off of there. So there are two kind of ways we do this. The way that we usually do it is we just break this integral up. So we can rewrite this integral really as the integral from negative infinity to 0, 1 over x squared plus 36 dx, plus the integral from 0 to infinity of 1 over x squared plus 36 dx. And so the idea is break it up into two different improper integrals that we've done before, and then do those separately. And then if they both converge, when you add them together, they have to converge. But this one's kind of special. Why? Well, notice this area on the left is actually the same as the area on the right. So we can kind of simplify this process by rewriting this as basically two of these. So it's going to be 2 times this limit as x goes, 2 times one of these integrals. So 0 to infinity of 1 over x squared plus 36 dx. So that's what we're going to do. We're just going to do 2 of them because they are the same integral. One's just reflected over the y-axis, basically. And so now we can rewrite this. So to make sense of it, we'll write 2 times the limit as not x, but as b goes to infinity. And we'll integrate this from 0 to b of 1 over x squared plus 36 dx. And so we took an improper integral to make it proper. We just introduce basically a dummy variable, b, and then we let b get bigger and bigger and bigger. And if this actually goes to something, we say that's the value of the improper integral. Now, how to do this integral? So this is a nice one. You actually have 2 choices here. You could do trig substitution, or if you see this, if you look at this and you're like, that's an inverse tan almost right there, you could do an inverse tan on it if you want to. For fun, I'm going to make it a trig substitution because I think it's good for us to practice it, and we'll do the inverse tan stuff later on. All right, so how do I use trig substitution on this? Well, it's not obvious, but that's like your square root squared. So what I can do is I can make my right triangle, which I'll do right here. So let's make my right triangle. And where do I put that x squared plus 36? Well, it's actually the plus puts it on the hypotenuse, and we'll make it a square root. And then I'll put the x here, and 36, of course, is 6 squared. So I'll put that right there, and there's my theta. And then what I can do here is I could say my tan of theta is equal to x over 6. And so 6 tan theta is equal to x. And then if I take the derivative here, I get 6, and then derivative tan theta is secant squared theta, and then d theta. And the derivative of x is just dx. And so I have my dx, I have my x. Now I need to find this guy right here. So that's a cosine of theta is equal to a 6 over, and then the square root here of x squared plus 36. I'll flip it, so I get secant of theta is equal to the square root of x squared plus 36 over 6. And then, of course, move that 6 over, so 6 times secant theta is equal to my square root. And I don't want the square root of x squared plus 36. I want this thing squared. So I'll square both sides, and when I square both sides, I get 36 secant squared theta, and then it's equal to then x squared plus 36. And I wanted that because I have it right there. And so this will be equal to then, what? 2 times the limit as b goes to infinity, the integral of, and here I have to make sure I change my limits of integration. So I'm going from 0 to b here. So what happens? What happens if x is equal to b? Well, that implies what? Well, I come down here, and that means my tan of theta is equal to what? B over 6. And so that tells me that theta is equal to the tan inverse of b over 6. So that's my upper limit. So tan inverse of b divided by 6. And then what happens when I'm 0? So x is equal to 0. That implies tan of theta is equal to 0 over 6, which is just 0. So that implies theta equals tan inverse of 0. And remember, tan inverse of 0 is just 0. It's like what angle when you take the tan of it to get 0 back. And so then the bottom limit is now 0. And now I can plug in for all my stuff. So 1 over. And so now I know what this is. This is what? This is this guy right here. So that's what, 36 secant squared theta. And then my dx is right here. And my dx is just this guy right here. And so that's a 6 secant squared theta d theta, which is nice because that means this is going to cancel with this, and this is going to cancel with that, leaving a 6 downstairs. And so down here, I have 2 times the limit as b goes to infinity, the integral from 0 to tan inverse of b over 6, and then of 1/6 d theta. I can pull that 1/6 out in front if you want. And so I'm going to get this to be 2 over 6, which is 1/3, the limit as b goes to infinity. And then here I just have the integral from 0 to tan inverse of b over 6, and of just d theta. You can put a 1 here if you want, but you don't need to. And I can integrate that, so it's going to be 1/3, the limit as b goes to infinity of what? Theta. So that's the integral of 1 d theta, evaluated from 0 to tan inverse of b over 6, which equals, and so this will be 1/3, the limit as b goes to infinity of what? You just plug in your upper limit. So I just get tan inverse of b over 6 minus, then plug in 0. And then we just talked about this limit a little while ago. So what happens? We'll plug in infinity here. So 1/3 tan inverse of infinity over 6. And so what is that? Well, remember, tan inverse of infinity is just pi over 2. So it's just 1/3 times pi over 2, which equals pi over 6. And then the question becomes, is pi over 6 the same thing or similar to the same thing that we found above? So let's just take a look here. Let's zoom out a little bit. Move this over. All right, so we have this, basically, we have this number here, 0.5036. And my question is pi over 6 kind of close to that. So let's check it out. So on my calculator, I'm going to hit second pi divided by 6 and see what I get. That's pretty close, right? 0.5235, so that's good evidence. So I think it's good to go. So again, this integral also converges. Right. Now, what we've yet to see is an integral that diverges. Um, it's not that hard to come up with integrals that diverge. So let me just give you a real quick example, because the example that where it diverges is the next one, which we'll do in the next video. But super easy example, guys. Like the integral from let's just do 0 to infinity of x squared dx. That's definitely going to diverge. Just check it out. What we'll do is write the limit as b goes to infinity of the integral from 0 to b of x squared dx. And of course, that's going to be equal to then the limit as b goes to infinity. We can integrate this. We just add 1 and divide by it, x cubed over 3 from 0 to b. Plug in our limits of integration. So limit as b goes to infinity. And then that would be b cubed over 3. And then minus 0 cubed over 3, which is just 0, but we'll write it down. And then as you go to infinity, you can treat infinity like a number and plug it in and interpret as long as you don't cancel. So you get infinity cubed over 3. And of course, that's just 0. And so that's equal to infinity. Right? So this integral right here diverges. Or you might say this integral is divergent. And that's it. That's all I have for us today.